So the greater the electronegativity difference, the greater the polarity, the stronger the bond. So if it's a strong bond too, we talked about on Monday that the bond length would be shorter, actually, so it's going to be a shorter bond. Whoops. So we're going to arrange the following bonds in order of increasing bond length. Are we missing something? Oh, you guys just don't have this. That's right. So we're going to, from shortest to longest. So what did we say the relationship between bond energy and bond length was? Think about the example I had when you picked up a stick from the yard. If you hold your hands closer together, does it take more energy? Farther apart's easier, so bond length that's long has low energy. So short, what's the shortest then? What's the shortest bond up there? HF, because it has the highest energy. And what would be the next? HCl, then HBr, then HI. Yes.
So HI is the hardest to break.
No, easiest.
But it's far apart over here.
That doesn't necessarily. Look at the trend though in the halogens. If the strongest is HF, and then it went HCl, then HBr, and then HI. Look at that trend that we have there.
Pretty much you're just following what they tell you on the numbers.
Yes, we're going from highest to lowest. The highest energy would be the shortest bond. So, the atoms want to have a full octet. They want to have 8 valence electrons, so they're stable like a noble gas, because noble gases all have 8 valence electrons. So they are going to form compounds that tend to form so that each atom, by either gaining, losing, or sharing electrons, has an octet in its valence shell. And those, if you have 8 electrons in the outer shell, they are stable. Now there's a few exceptions. Like hydrogen and helium are stable with just 2 electrons, because if we look up at the periodic table and we think about their orbital notations, they have hydrogen and helium are both in the first energy level. And does the first energy level have a p sublevel? Do you have a 1p? No, it's only 1s. So to fill its first energy, its highest energy level is 1. To fill that energy level, you only need 2 electrons. So it's stable with just 2 electrons. Boron can form bonds and be stable with just 6 electrons. Same with aluminum. Boron and aluminum are able to form bonds and be stable with just 6 electrons. Beryllium can be stable with just 4 electrons. So those are some exceptions to the rule of the octet rule. So to show these valence electrons, we draw what's called an electron dot structure. That's misspelled up there, isn't it? Structure. The notation in which only valence electrons in an element are shown with dots. So we'll have the element symbol written, and then we're going to draw the valence electrons with dots. So here's an example, neon. And the order you want to draw them, electrons repel each other, so they want to be as far apart as possible. So the first dot you'll draw is here. The second dot should be opposite it. You could start on the left and right, but just as long as you put the second dot opposite, that's where you'll want to go. 1, 2, and then 3 and 4, and then 5 and 6, 7 and 8. And you can go left, right, up, down. As long as you're going opposite each other, they will be fine. 4 and 7? That's because we filled 1, 2, 3, and 4, and then we fill in the sides again, 5, 6, 7, and 8 then.
So then you go 1, 2, 5, 6.
No, you'd want to fill 1, 2, 3, 4. You'd want one on each side first before you'd fill the second. Kind of like when in orbital notations where we put the arrows and you filled one orbital first and then filled the second orbital. Same with this, same idea where you'd want to put one dot on each side before you put the second dot on that side. So sodium has how many valence electrons? What's the highest energy level sodium is in? (3s). So if the third energy level is its highest energy level, how many electrons are in the third energy level? How many electrons? Just one electron, right? 3s1. One electron. So how many dots would we have? One. That's all you'd have to do. Put one dot on it. How about chlorine? Chlorine's highest energy level is what? Chlorine's right there. So, but at the energy level is the third energy level. So how many electrons are in the third energy level? Yeah, 7. We have 1, 2, 3, 4, 5, 6, 7. 3s2, 3p5. You add those together and you have 7. So we need to fill in 7 electrons. So we're going to fill opposite each other first. 1, 2, 3, 4, and then 5, 6. And then the 7th one could really go on either side. It doesn't really matter. We'll put it right there. How about krypton? Krypton is right there. So the highest energy level it's in is 4. How many electrons are in the fourth energy level? Is this the fourth energy level right here? That's the third energy level. So we don't count those. So you just have 1, 2, 3, 4, 5, 6, 7, 8. So it has a full octet. We still should be in the habit of just filling 1, 2, 3, 4, 5, 6, 7, 8. So there's krypton. How about boron? Boron's number 5. So what's its highest energy level? 2. So how many electrons are in the second energy level? 3. 1, 2, 3. 2s2, 2p1. That third one could be either side. Or if you go left, right, it could be on the top or bottom. That part doesn't really matter. No, you just one dot on each side at least. You can't have 2 dots together. Hydrogen has how many valence electrons? 1. That 1 could be on any side, any of the 4 sides. How about nitrogen? 5, yep. So we have 1, 2, 3, 4, and then the 5th one could go on any side. I'll just put it up here. Sulfur. Okay, the highest energy level is 3. We have 3s2, 3p4. CS, we have 6. 1, 2, 3, 4, 5, 6. Those last 2 just need to be opposite each other. And then barium. Where is barium? Right here. So what's its highest energy level? 6, and it's in 6s2. So how many valence electrons? 2. So as long as they're opposite each other, it could be left and right, top or bottom. That doesn't matter. Questions on finding the valence electrons? Do you remember doing this in physical science? A lot different. Oh, really? Circles? I think that's different.
That's electron configuration. Damn.
So when, oh,
Dots are only paired when what?
when each side is filled, put that in there. So we are going to draw a compound and show where the electrons are at. We're combining two or more electron dot structures and we're going to show the shared electrons and the unshared electrons. So this is an example of F2. So we have unshared or lone pairs are the electrons that are not being shared. The shared electrons are the electrons in between the two elements. So we'd have these two electrons that are in between are shared between each fluorine. So they're sharing those two electrons. This is going to indicate the number, arrangement, and the kind of bonds. And whenever you have shared electrons, you represent them by a dash. So one dash represents two electrons. And let's go through how you would get this Lewis structure. So we would want to write the two fluorines first, and fluorine has how many valence electrons? 7, right. So we're going to draw 7 electrons around this fluorine. 1, 2, 3, 4, 5, 6. Now just something you'll figure out as we go. The 7th one, since I'm going to probably share an electron here, I want to leave this side as having just 1 electron. I'm going to put the 7th electron here. So if there's an atom that's in between or next to another atom, you'll probably want to leave that with either 0 electrons or 1 electron on that side. So that way it's able to share. So this fluorine, we have 1, 2, 3, 4, 5, 6. And same here. I don't want to put a 3rd one here because it looks like they're going to just share these electrons. So I'm going to put the 7th one over here since that side has a spot open. So now these 2 electrons are those shared electrons. Sometimes it's easier. This is not, I mean, it doesn't have to be drawn this way, but it's easier if you leave them like this direction instead of on top of each other, because otherwise you have to erase them and then you're going to draw a dash. So I can just make that a dash if I leave them horizontal of each other, or at least that direction.
So the dash represents 1 on one side and 1 on the other side?
A lot of times that's how it'll be. It just means they're sharing 2 electrons. Those 2 electrons could come from the same atom. So fluorine could have shared 2 of its electrons with this fluorine. There's going to be some compounds where it'll share 2 electrons, not just 1. This could also be drawn like this, and it would be the exact same thing, but you could draw it vertically. It doesn't matter. Okay. Make sure you do show the extra dots because those are the lone pairs of electrons. And then change that into a dash. What formula? Is there a blank? I don't know. Cross it out. I don't know what it was. So when we draw Lewis structures, just a few guidelines that you should follow. The least electronegative atom is central. So when you look at your electronegativities, you'll want the lowest number, usually is in the middle. Except hydrogen. Hydrogen is always around the outside of the compound just because it can only
it's stable with only 2 electrons, it can only have 1 bond. It can't have 2 bonds. So it can't be in the middle of 2 atoms because it can't form 2 bonds. It can only form 1 bond. And then just as a rule of thumb, carbon is almost always central. So if carbon is in your compound, almost always put carbon in the middle, surrounded by other atoms. And we can also show multiple bonds. So if we have a single bond, we have 1 dash. Double bond would be 2 dashes. How many electrons would need to be shared in order to have a double bond? If we have 2 dashes, that means how many electrons? 4 electrons, right? Because each dash represents 2 electrons. If it's a triple bond, we'd have 3 dashes with how many electrons shared? 6 electrons. So to draw the Lewis structure, you're going to determine the total number of valence electrons in the compound, add it all up, then arrange the atoms' symbols to show how they're bonded, and then you'll draw your valence electrons in as dots. Then you'll want to count how many dots you drew to how many you should have that you calculated in number 1. If it's correct, then you'll just change the electrons that are being shared into dashes, and then make sure at the end, with the exception of hydrogen and those other exceptions we had were boron, aluminum, and beryllium, make sure that they are following the octet rule. So they should have 8 valence electrons around them. And those shared electrons, you count as valence electrons for both atoms that are being shared with it. So I think we're ready to do a few more examples. Can I switch it? Not quite.
So like this CH3L and it's connected with 3 dashes.
It's an I, yeah. Well, let's... Which atom should be in this, was the central atom between CH and I? Carbon. Carbon should always be your central atom if it's in the compound. So now I'm going to write the H. We have 3 H's, and then we have that's an I. Yep. So the first step that we wanted to do, actually this was the second step. We should first add up the valence electrons. So carbon has how many valence electrons? 4. And how many does hydrogen have? So, and we have 3 hydrogens, so we're going to take 3 times 1. Plus, how many does iodine have? 7. Yep. So we get a total of 14 electrons. This is how many dots we should draw. But now let's go around and draw in dots around the atoms. So carbon, we said, had 4 valence electrons, so let's draw 4 dots. Hydrogens each had 1. Where do you think it makes the most sense to draw their 1 electron? For this hydrogen, we should put it on. Should I put it up here? No. I should probably put it in between the 2 atoms since they're probably going to share that electron. Same with this hydrogen. I probably should put it in between, and this one I should put in between because they're probably going to share it. And then iodine has 7, so I have 1, 2, 3, 4, 5, 6. Now this, we don't want to put a 3rd electron in between carbon and iodine. This one has a spot open, so I'm going to put one there. So now I want to count up how many dots did I draw. I drew 2, 4, 6, 8, 10, 12, 14 dots, which is equal to how many I added up that I should have. So now I need to change the shared electrons into dashes. This is why it's kind of nice to draw them in that manner. You can have the 2 dots drawn like on top of each other here, but then you'd have to erase them and draw the line in. And now I want to check the octet. That was the last step. So carbon has how many valence electrons around it now? Each dash represents 2 electrons. So I have 2, 4, 6, 8 valence electrons. Hydrogens each have 2, which hydrogen is stable with 2. Iodine has 2, 4, 6. And 8. I forgot to count the shared ones. So 2, 4, 6, 8 electrons. So it also has an octet. So I would say this would be the correct Lewis structure. Let's do one more. NH3, nitrogen has how many valence electrons? 5 plus, we said hydrogen each have 1, so we have a total of 8. Which element should be in the center? Nitrogen, because hydrogen never will be in the center. So now we have 3 hydrogens around it. Nitrogen, we said, has 5, so let's put 1, 2, 3, 4. Now where should we probably put the 5th one? I would say on the bottom. Just by looking at this, hydrogen is going to donate 1, and that will fill the sides on each of these sides, and we'll put the 5th one here. Now, you could have this top hydrogen on the bottom. You could have one at the right or left on the bottom. It doesn't matter which side the hydrogens are on, as long as you have 1 on each side. And then each hydrogen donates 1 here. So now I have 2, 4, 6, 8 dots, which is the number I calculated in that first step. So let's change them into bonds, those 3. And nitrogen also has an octet. Hydrogen each have 2, so they're stable. So that would be our Lewis structure. What? So to